Okay, today we're going to do the last important concepts of kinetics, changing K and catalyst. The first one, changing K, introduces an equation called the Arrenehius equation that is not going to be a part of what we will be doing in this class. It will not be on the test, but you will see it if you take intro-level chemistry in college. So I'm going to make sure that you see it. And then the most important concept here is called catalysts. So let's go forward from here. So we need to be able to understand these concepts in terms of what we've got going on in an energy diagram. And you guys all know what we're talking about when we say an energy diagram. This is not brand new news here. Okay, don't do anything that I'm telling you to do. So energy diagram looks like so, where we have time going by or some sort of that, something like that. Why are you acting so funny right now? This is interesting. Okay, and then we have the initial potential energy of the reactants and the potential energy of the products. Remember, that's what we were most concerned with when we were talking about thermodynamics, the beginning and the end, nothing in between. And when we take the difference between the products minus the reactants, remember products, sum of the products minus the sum of the reactants gives us the delta H. Yes, it's being crazy right now. I don't know why. Okay, so we know how to do that. The activated complex, well, the activated complex is the thing that happens at the top. So up here, we have the activated complex that occurs right there. The activation energy is the difference in energy between where the reactants are and where the activated complex is. This is the EA. Okay. Do we recognize if this is endo or exothermic? And that is determined by where the reactants are and where the products are. In this particular case, because the products are lower than the reactants, it will be a negative delta H, which means it's exothermic. If it's the other way and the reactants are lower than the products, then it would be endothermic. And then what would happen in the reverse situation? So if this is where we started and this is where we ended, the reverse of the reaction. So all of those things you guys are pretty familiar with and we've talked about at some point in time in passing. Okay, so remember, molecules must collide. They must collide with the right orientation and they must collide with the right amount of energy. This is the kinetic molecular theory, also known as the KMT for short. But these things must happen in order for reactions to occur. So we know they have to collide, but they also have to collide with the right orientation in the right way, in the right direction, in the right geometry, and they have to have the right amount of energy in order to be able to react. Without those two things and without collisions, we have no reactions happening. So what messed up the rate law equation? Increasing the concentration changes the rate by increasing it. More things to collide. So again, when we change the K or the rate law, we change it by increasing those things that would cause more collisions to happen. So this isn't a brand new concept. It should be a concept that you have. Increasing rate means I'm going to have more ways to collide in the right directions. Okay? So K stays the same regardless of the amount. You need to keep the same reaction. If you change the reaction, you change the K. So as long as you keep everything the same in the reaction, K stays the same. The moment you start changing things, K then changes. Okay? How can K be changed? If I change the temperature, if I increase the temperature, that increases K exponentially, which will increase the rate. By the way, remember, this is all in your notes already. You should just have to annotate the stuff. Okay, next, if I change the activation energy, if I increase the activation energy, I decrease K. So if I change the amount of energy that is needed or decrease the amount of energy that is needed in order for the reaction to occur, then K changes. If I add a catalyst, adding a catalyst decreases the activation energy. Adding a catalyst decreases the activation energy. It creates an alternate pathway, and we'll talk about that in just a minute. So this will also change K. Because the rate is increasing, K will also increase. So the Arrhenius equation helps us understand K, because as you can see in the Arrhenius equation, we see K right here. Oops, I'm writing on the wrong thing. We see K right there. And it's equal to A times E to the negative EA. What is EA again? Activation energy divided by RT. What are R and T? No, R is not rate. R is the gas law constant. Okay? R is the gas law constant. Okay, so we've got the gas law constant and temperature as a part of this. If we can manipulate it a little bit to get rid of this E, this exponent, how do we get rid of an exponent mathematically? We take the natural log of it. So when we take the natural log of this, we get the natural log of A coming out by itself added to this EA over R times 1 over T. And if you look, it does the same thing. And so basically, guess what we just have? We have another y equals mx plus b graph, where we've graphed the natural log of K over A. And A is usually a concentration issue. It's something. Okay? And then we get negative EA over R is the slope of the line. And we have the natural log of K versus 1 over T. So the reciprocal of temperature. So basically, we know that negative EA over R is equal to the slope, boy, that is bad, slope of the natural log of K versus 1 over temperature graph. Okay. So now we have a way to find activation energy for a reaction. That's also a really key here, because if we know the slope of the line, we can find the activation energy for the reaction as well, because we have a way to do that using that graph. Now I'll say this again, the Arrhenius equation is beyond this test. You will notice that the Arrhenius equation is not on your purple sheets, your guide sheets that I gave you at the beginning of the school year. That is because you will not have to use the Arrhenius equation. However, you will see this in college. How do I know this? Because I've had people come back and say, remember that thing you said wasn't on the test? I saw it when I was blah, 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 working it, blah, 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 blah. Okay? So it will come back, and you will see it if you have General Chem 1 and 2. So here we go. Just saying the exact same thing as what I just said there. The slope is equal to negative EA over R, and it's the slope of the natural log of K versus 1 over T being temperature graph. And so it gives us a really easy way to find activation energy. Now, I have given you some problems on the Arrhenius equation on problem set 5. Why? Because I want you to have exposure to it. Is that something that you should super focus on? No. Why not? It's not going to be on the AP test, but it's something that you'll want to get used to. So acid-base catalyst work by causing a reaction to gain or lose protons. So it allows for reaction to occur more quickly by chemically changing a reactant. So if we look at this, and we look at the one that's in black here, we look at this one right here. It is the methyl trimethyl kind of thing going on here. It's actually methyl 2-methyl propyl something or other. I don't know the official names of all of this, but that doesn't look like an acid, does it? Does this thing look like an acid? Does this thing look like an acid in red? It's got lots of H's, but if we add an acid and get this H plus extra here, then we can cause something to lose an H. So what's happening here is this guy right here is losing one of its hydrogens, so that then he can bond by taking one of the hydrogens here. Actually, it flips over. It stays the same. We get rid of this double bond, and we attach it right here. So it occurs more quickly when we add an acid-base catalyst. Catalysts can be a lot of ways, but acid-base catalysts are one of them. Surface catalyst works by allowing molecules to adsorb on a surface at active sites that are particularly good for the reaction, providing collisions that are more effective by controlling their orientation. So basically, this idea using a surface catalyst, that usually means a solid metal, is because what we can do is we can get a chemical to stick to that metal, adsorb to that metal, in the exact orientation it needs to absorb, in the exact orientation it needs to orient, so that when it's hit by something else, I can get collisions to happen more frequently that are going to have that reaction occur. Absorption is sticking to the surface. The active site is a place on the surface where reactants can stick and where bonds between reactant molecules are weakened. So basically, we stick to the surface of the catalyst. We stick in an orientation that we're going to be able to react really well in, that weakens any bonds that need to be weakened, so that when the next thing comes along and hits us, it reacts in the exact right orientation with the exact right energy, because we've reduced that amount of energy, and we can make that product. A place where this happens a lot is your catalytic converter. Because remember, when your car is running, it's running and it's going through incomplete combustion. And there are other things there. So your car is making CO and it's making NO. And neither one of those two are really great things for the environment. Okay? So what can we do? Well, we can create the system where a platinum catalyst will take one of these two, a CO or an NO, and make it absorb to it, weakening the bonds between the carbon-oxygen or the nitrogen-oxygen, so that when one of these two comes out, what we end up getting is we end up getting CO2 plus N2, which are naturally occurring gases in the air already. Okay, that's the process that happens. But you have to have this platinum catalyst, which is why catalytic converters are so expensive, in order for this to happen, because the platinum causes one of them to stick to the catalytic converter. So here we have a nickel absorptive surface, and we see that ethene is sticking to it, and we can see the two carbons of the ethene are sticking to the nickel surface. And we see that we have this other molecule, it looks like a hydrogen molecule, coming in and absorbing too. And what it allows it to do, and remember, ethene, I'm going to remind you, ethene, because of the ene ending, not the ane ending, means that we have carbon double bonded. Okay, ane means a single bond, ene means a double bond, yne, Y-N-E, means a triple bond. So basically what's happening is this nickel, these two carbons stick to the nickel and weaken that double bond, causing it to come down and have a site for a single bond. The hydrogen then comes in and splits apart.
Will you call me at 2616, Mike husband?
Sorry about that. The hydrogen comes and splits apart and then is allowed to very easily bond to the ethene in that single bond site that it can get there. Okay? And then leaving a space in the surface where more ethane can come and join and hydrogens can come and join. So basically this nickel catalyst helps to make this reaction occur faster. Will it occur naturally? Probably. It'll take a long time though. If we want it to occur faster, we give it an alternate pathway, and this is what this is doing. Basically, when the carbons stick to the nickel, weakening that double bond between the carbons, causing it to be prepared for single bonds. Hydrogen comes along, splits up, adds itself in, then this breaks free. Once this one's done, it breaks free, leaving behind two hydrogen atoms and a space for another ethene to come along. Does that make sense? Okay, so that is a surface catalyst. Enzymes. Now, you looked at enzymes last year. Some of you are like, I don't remember any of that. Biology sucked. Okay, hang on just a second. So in biology, you probably learned a lot about enzymes, and I know some of you are like, I didn't learn anything about enzymes. So let's see if we can do this thing here. I might have to get off and come back out and show discard that. Okay, and then I want to go over here because I have it up over here. All right.
Every organism, enzymes. Through enzymatic action, your metabolism's driven. Enzymes. In Staphylococcus, jellyfish, tarantulas, and trees, they lower activation energy. Enzymes. And you and me now, enzymes. You got them in your cells where they do cellular digestion. Enzymes. You got them in your mouth and in your stomach and intestines. Enzymes. The thing an enzyme acts upon is called a substrate. They fit like lock and key with complementary shape. Enzymes speed up reaction rates. Enzymes. An enzyme binds its substrate at its active site. Enzymes. Bound together in a complex where they snuggle so tight. Enzymes. New bonds will form and break through to the active sites. Chemistry reactants become products. It's an enzyme specialty. Product gets released. Enzyme repeats its action readily. Enzymes. Like any molecule, an enzyme shape defines its function. Enzymes. Environmental changes shape leads to malfunction. Enzymes. Every enzyme has a pH where it catalyzes best. A pH change will set enzyme activity to rest. Enzyme also sensitive to easily upset. Enzymes. Raw heat until a certain point increases their efficiency. Enzymes. But too much heat denatures them, destroying their activity. Enzymes. That's why a fever running high is a dangerous situation. All that heat can alter enzymatic conformation. Keep it 98.6 for enzyme optimization. Enzymes. Enzymes in saliva will break starch into glucose. Enzymes. If you lack the enzyme lactase, then you won't enjoy milk lactose. Enzymes. Taste galactosemia and PKU disease caused by inherited enzyme deficiencies. Enzymes, they're what everybody needs. Enzymes. Enzymes.
Okay. Get your dad. All right, so basically what we need to really understand about enzymes is this idea that every enzyme works in a very specific way. It's called lock and key method. Yeah. So the lock and key method allows for the activation energy to be lowered. And because of that, reactions occur much more quickly. In fact, almost all biochemical reactions that occur in our body are slow, really slow. And the only way that they can actually occur to an efficient time frame is by use of enzymes. And there are so many enzymes that are running around our body at any given time. Insulin, in fact, is an enzyme. Catalase. Catalase is the enzyme that allows for hydrogen peroxide that is produced in our cells naturally to be destroyed because peroxide is a poison. So that's why when we put peroxide on things that were bleeding, it bubbles because catalase is inside your blood to actually alleviate the hydrogen peroxide that's naturally produced in part of the cellular process. Every process has an enzyme that is very specific, and the enzyme has an active site that binds to the place where it needs to be able to work, and anything, pH changes, temperature changes, can cause them not to work anymore. That's why your body has to be in a very, very specific pH range. Your body has to be in a very, very specific temperature range. Outside of those ranges, your body doesn't function and you don't produce the things that you need to produce to be a healthy person. The diseases he mentioned, Tay-Sachs, PKU, are all diseases that are caused genetically by not producing a specific enzyme that then causes the body to do something that needs to be taken care of. So the more we research genetically, the more we start understanding these diseases that we've seen for years and years and years, and the better we can be able to treat them. So enzymes are another form of catalyst. They're just our biological form of catalyst. Okay. So we start to see what's happening here. We can see the enzyme sucrase takes sucrose and it breaks it apart, breaks that bond between the glucose and the fructose. apart to make a glucose and fructose. Then fructose will later be made into glucose. Basically, fructose is a 5 sugar ring and glucose is a 6-sided sugar ring. That's basically it. And sucrose is one of each bonded together. All right? So that is it for this one.